To understand the carry select adder, you must first understand the limitation it was designed to overcome. In a ripple carry adder, full adders are chained in series. The carry output of each stage feeds directly into the carry input of the next. For an n-bit addition, the final sum cannot be computed until the carry has propagated through every stage in sequence, from the least significant bit all the way to the most significant bit. This carry propagation delay grows linearly with the number of bits. Double the word width and the worst case delay doubles. For wide data paths, 32-bit, 64-bit or wider, this becomes a significant timing bottleneck, directly limiting the maximum clock frequency of any system that depends on addition in its critical path. The carry select adder breaks this linear dependency. It does so through a straightforward but powerful observation. The carry into any group of bits is always either 0 or 1. There are no other possibilities. So rather than waiting for the actual carry to arrive before computing the sum, we can compute both possible results in advance simultaneously and then simply select the correct one the moment the actual carry is known. Selection is fast. A multiplexer is far faster than a carry chain. This is exactly what the schematic in front of you implements. This is a 4-bit carry select adder. Read the schematic carefully and systematically. The input bit pairs A0 B0, A1 B1, A2 B2 and A3 B3 are shown entering from the top. Notice that these inputs fan out downward into both rows of full adders simultaneously. Both rows receive identical data inputs. This is the defining structural feature of the carry select approach. There are two rows of 4 full adders each, as shown. The top row has its carry input fixed at 0, labeled Cin equal to 0 on the right side of the schematic. This row computes the sum of A and B under the assumption that no carry is coming in. The bottom row has its carry input fixed at logic 1, labeled as Cin equal to 1. This row computes the sum of A and B under the assumption that a carry of 1 is incoming. Both rows begin computing the moment A and B inputs arrive. They do not wait. They run in parallel, producing two complete sets of candidate sum bits and carry outputs simultaneously. At the bottom of the schematic are four multiplexers, the trapezoidal symbols, one for each sum output bit S0, S1, S2 and S3. Each multiplexer receives two candidates values, the sum bit from the top row assuming carry in 0 and the sum bit from the bottom row assuming carry in 1. The actual Cin signal shown on the green horizontal line at the bottom is the select line fed to all four multiplexers simultaneously. On the left side, a single large multiplexer selects the final Cout, again choosing between the carry output of the top row and the carry output of the bottom row controlled by the same actual Cin. When the real Cin arrives, all multiplexers switch instantly to select the correct pre-computed result. The sum bits S0 through S3 and the final carry out are produced with minimum additional delay. just the propagation delay through multiplexer itself. The critical path delay of this carry select adder has two components. The first component is the time required for the two rows of full adders to complete their parallel computations. Since both rows start simultaneously with the arrival of A and B, and each row is itself a 4-bit ripple carry chain internally, this delay is the propagation time through 4 full adders in series, the same as a 4-bit ripple carry adder. This computation runs in the background while the actual carry in is still in transit from upstream logic. The second component is the multiplexer select delay, the time from when the actual C-in arrives to when the multiplexers output the correct selected result. The total worst case delay is whichever of these two components finishes last. In a well-designed system, the full adder computation time and the carry in arrival time are balanced so that the carry arrives approximately when or slightly before the full adder rows have finished, making the multiplexer delay the only additional cost beyond the parallel computation. Compare this directly to a ripple carry adder of the same 4-bit width. A ripple carry adder must wait for carry propagation through all 4 stages sequentially. The carry select adder replaces the sequential carry wait with a parallel pre-computation followed by a single fast multiplexer section. For wider adders built from multiple carry select groups, the saving compounds significantly. The architecture shown here is a single 4-bit group. In practice, carry select adders are built by chaining multiple such groups to cover wider word widths. The carry output of one group's multiplexer becomes the actual carry input select line for the next group's multiplexers. Each group computes both its 0 carry and 1 carry results in parallel during the time the previous group's carry is propagating to it. An important refinement used in industry is the variable group size carry select adder. Because the carry's propagation delay from earlier groups gives latter groups slightly more pre-computation time, latter groups can be made wider without adding to the critical path. This allows large adder to be built with fewer total full adder cells than a naive uniform group design would require, optimizing the area delay trade-off. In modern ASIC and processor design, the carry select adder presents a practical middle ground between the simplicity of a ripple carry adder and the complexity of a carry look ahead adder, or its tree-based derivatives such as the Cogstone or Brent-Kung architectures. It achieves meaningful delay reduction with a straightforward regular structure that maps cleanly to standard cell, place and route flows. The area cost approximately double the full adder count due to the 2 parallel rows is a known predictable trade-off against the delay improvement. In data paths where addition is on the critical timing path and where the area overhead of a full look ahead architecture is not justified by the performance requirement, the carry select adder remains a relevant and widely used design choice. The carry select adder solves the carry propagation bottleneck not by computing carry faster, but by eliminating the wait for carry entirely. By pre-computing both possible outcomes in parallel and using a multiplexer to select the correct result the instant the actual carry is known, It converts a sequential delay into a parallel computation followed by a fast selection. Reading this schematic correctly requires understanding three things: that both FA, that is full adder rows, receive identical data inputs and run simultaneously, that the top row assumes carry in 0 and the bottom row assumes carry in 1, and that the actual carry in drives the multiplexers to select the correct pre-computed result at the final output stage. That is the complete accurate picture of what this circuit does and why it does it.